Hello, I'm Václav Novotný and welcome to the tutorial of Decentralized Systems 1. This tutorial will be focused on combined heat and power systems, particularly based on Stirling engine and internal combustion engines, and we will look at their balance models. So we will start with Stirling engine cogeneration systems, or actually, as you can see here, micro cogeneration systems, because the Stirling engine systems are basically of the lowest power output spectrum. And how the whole system works can be illustrated on the few pictures we have here, where this is biomass fired system with the pellets over here. Here some pellet combustor which directly heats up the hot cylinder of the Stirling engine. Then the cold cylinder of the Stirling engine takes place of the heat rejection into the heating water. A system like this can be of power output, let's say, in order of single or few kilowatts. Then you can have something similar, but for combustion of natural gas, which is a product that made it into serial manufacturing. As we can see the product here from company Remeha, where inside of the system there is the standard natural gas boiler, and then there is the Stirling engine system, which is actually based on 3-piston Stirling engine. Both of these systems had power output of about 1 kilowatt electrical. And for the higher power outputs, we can see over here a system with electrical output about 35 kilowatts that uses gasification combustion of wood chip biomass, where the combustion chamber and gasification and combustion integrated chamber is ended out by this module with the heat exchangers, which then go into the Stirling engine itself, which is built inside of this green steel vessel. Now here we have the ideal thermodynamic cycle of the Stirling engine in the PV and TS diagrams, where in the PV diagram we can see that there are two changes that are isochoric, taking place at constant volume, and then, for example, in the TS diagram we can see that the other two changes are isothermal. So the isothermal change, you know it, for example, from Carnot cycle. And the isochoric change, if we have ideal gas with constant specific heat capacity, or the heat capacity very similar at different temperatures. So the heat that would be rejected during this change 2 to 3 over here can be regenerated to the change 4 to 1, and by that we get just the isothermal heat addition, isothermal heat rejection, and it can be considered, or it is sometimes described as generalized Carnot cycle. The real Stirling cycle, however, looks a little bit differently, where here we have illustration of the ideal cycle in the PV diagram with the isothermal and isochoric changes, then isothermal expansion over here and the isochoric heat rejection. But the real cycle, due to limits like heat transfer, the actual kinematics of the system, pressure drops within the system, and so on, is far, or quite far, from the ideal one. So now let's see in detail how the Stirling engine actually works. How is this cycle realized, or how we try to build systems with the Stirling cycles. So typically Stirling cycle can be made in so-called alpha, beta and gamma configurations, where here in the alpha configuration we have 2 pistons in 2 separate cylinders, where we have the hot cylinder and cold cylinder. Into the hot cylinder we have the heat addition. Then there is isochoric change, where one piston, the hot piston, pushes the hot gas through the recuperator into the cold cylinder, and then during the heat rejection the cold cylinder moves downwards and we have isothermal heat rejection. The change is isochoric, and ideally in the tubing between the first and second cylinder we have some heat absorbing material which has very high heat transfer, very high heat capacity, and very low pressure drop. Now you can already hear that probably there will be some catch in the fact how to do this in real life, but some material like this that would store the heat from going from the hot to the cold, and then again take the heat and heat up while going to the hot cylinder. The second configuration, the beta configuration, uses only a single cylinder with two pistons, and again we have the hot part, then the working fluid, the gas, moves towards the cold part, again ideally isochorically, and the recuperator would be either in the space between the pistons or integrated into the lower piston. And here we have the configuration gamma, where we have so-called expansion piston and compression piston, where the heater and cooler and the regenerator are all placed in the cylinder with the expansion piston, and when the compression piston is on the top part, basically all the gas is moved into the expansion space where the heat is added, and then when the working fluid is transferred into the compression space, into the compression piston, so the cooler over here takes care of the heat rejection. All these systems used some crankshaft or some other kinematic linkage into the rotational movement, but to make the electricity it does not need to be the case. We can also use linear generator, as we have over here, where you have basically a modification of the beta configuration, and the pistons are attached to springs, while on the shaft of one of the piston are placed magnets which move in the space with the electrical coils, and as the magnet moves along the coils, it creates it induces the voltage and creates electrical power. This configuration is called 3-piston Stirling engine. Now the real Stirling engine systems are typically of power output, let's say 1 to 50 kilowatts of electricity. So you can see really relatively low power outputs. The electrical efficiency can be between 10 to definitely no more than 30%. And in the cogeneration applications, the maximum efficiency, when we consider natural gas fired systems, can be which are in condensing mode, so the total efficiency can be up to a little bit more than 100% with respect to the lower heating value. As I mentioned, the fuels for these systems can be typically natural gas or biomass, where with the natural gas there is typically added peak burner, because these systems are rather expensive and you want this system to run as much as possible, and when you have some short peak demand, it's better to use some additional system than to oversize the Stirling engine system. Now, as you can also see here, the Stirling engine was quite complicated mechanism, so even though we had some applications shown over here, so most of them did not actually succeed much commercially, and after a few years of some trial operations, the manufacturing most of them was discontinued. But still, we will calculate an example of Stirling engine energy balance model, where we have at first a task: what is the thermal and total efficiency of 1 kilowatt electrical Stirling engine system, where the manufacturer's information say that the electrical efficiency is 18% and the nominal total efficiency in combined heat and power production, that means electrical plus thermal, is 105%. And the first question which we have here is: what is the nominal temperature of the heating water inlet? And it aims at the fact that it's a condensing system, like condensing boiler, and in order to have this high efficiency of the either here total efficiency or for condensing boiler efficiency of heat production, we need to be able to cool down the flue gas to really low temperatures. Let's just see an illustrative diagram where we have relative efficiency over here, then absolute efficiency over here. The relative efficiency is with respect to lower heating value, absolute efficiency is with respect to the higher heating value. Then here at the x-axis we have temperature of the flue gas at the outlet of the system. Over here we have illustrated enthalpy of the flue gas at the outlet of the system, and here the total usable enthalpy difference of the flue gas per kilogram of theoretical flue gas. And we have several lines in here, where the bottom line is for alpha equals 1, that means oxygen excess being 1, combusting just enough of air to burn all the oxygen with all the fuel. And then we have lambda 1.5, 2 and 3 for higher oxygen excess. And all these lines are for natural gas combustion. Then over here we have some other line, where intersection of the straight line with this curve going down is the dew point of the flue gas. So at this point the water in the flue gas would start to condensate. So if we have a look at the alpha equals 1, the oxygen excess of 1, we have the dew point at about 58 degrees C. As we increase the oxygen excess, the partial pressure of the water vapors would be lower, so it will cause the decrease of the dew point temperature, so the condensation would start later on. Also, as we have more air, so we are increasing the so-called stack loss. So when we cool down the flue gas to the same temperature, let's say 60 degrees C, we would have higher stack loss, so we would have lower efficiency over here than if we have the oxygen excess just 1, and we would have higher efficiency over here. Now, if the lines would be just straight, so it would mean the water would not condense, but in the beyond or below the dew point, the water would condense. And in our task, we had the total efficiency of 105% with respect to lower heating value, so it's the value over here. Now let's go into the detailed figure. 105 as the relative efficiency, or efficiency with respect to lower heating value, is, according to this diagram, about 95% or a little bit below 95% of the efficiency with respect to higher heating value. And the Stirling engine system would most likely have the oxygen excess a little bit higher than 1, but maybe not that much. So let's say that it would have oxygen excess of somewhere between 1 and 1.5. So it would be point somewhere over here, where there would be line in between these two. and that would mean that the flue gas at the outlet of the system need to have temperature of about 45 degrees C. That's already quite cold, and we still need some minimum temperature difference to be able to transfer the heat from the flue gas into the heating water. So if we consider at least 10 degrees C as temperature difference, so the heating water inlet temperature will need to be 35 degrees C. And with 35 degrees C, it's quite obvious that it is applicable like this into just into some low temperature heating systems where we really can cool down the temperature to this much. So in residential or accommodation applications, you would need to have systems like the floor heating, which is suitable for such low temperatures. So now, for continuing in our calculation, we will assume that the heating water goes from 35 degrees C at the inlet to 70 degrees C at the outlet. And the second task is to calculate all major streams going in and out of the system. When this system is applied, meaning 1 kilowatt of electric output and about 6 kilowatts of thermal output, you want it to run as long as possible. So for some peaks in the heat demand, we would have a peak burner. So the second task is to calculate the efficiency of the whole system when this peak burner would be in operation, and we will assume that the efficiency of this peak burner, as it's made just to deliver power output quickly, would be a little bit lower, about 90%. So this will be an example of quite basic balance calculations, where we have the Stirling engine combined heat and power unit. We have the fuel input into it, and the fuel is transformed to the work output, to the heat for heating, and to additional loss in the heat. So now let's summarize the input parameters. The net work output, or electrical output, was 1 kilowatt. Then we had specified the net electrical efficiency of the system, which was 18%. Then we had the total efficiency of both combined power and heat production. So total, or eta CHP, for nominal operation. And with respect to the lower heating value, so it was 105%, because it's a condensing unit which is using also some of the condensing heat. Then we had the temperatures of the heating water. So temperature of the heating water at the inlet was 35 degrees C, and temperature of the heating water outlet was 70 degrees C. And lastly, because we had specified that the system is using natural gas as a fuel, so we should also specify here the lower heating value of the natural gas. Like this, LHV natural gas, which is 50 megajoules per kilogram, or also if we would consider normal cubic meters, which is typical invoice value for natural gas, so it is 35.8 megajoules per normal cubic meter. So what we have specified from the streams in our simplified balance model, we know the electrical power output. It's the 1 kilowatt over here. So from that we can obtain, by using the efficiency over here, we can obtain the heat input in the fuel. So Q in will be the electrical power output divided by the efficiency in which the fuel input is converted to this power output. So this small CHP system requires 5.6 kilowatts of heat in the fuel when the heat is calculated with respect to lower heating value. Now this is the heat flow. Let's also calculate it as mass flow rate of the fuel. So it's the heat input in kilowatts divided by, and now it's the 50 megajoules per kilo, and if we want to the same units, so we need to multiply it by 1000 so that we get kilojoules per kilo. So it's kilowatts divided by kilojoules per kilo, and we get kilograms per second, because kilowatts are kilojoules per second. So it's kilograms per second, or we can have also the grams per second like this. Then, because the natural gas is typically paid by based on the consumption in standard cubic meters, so we can also calculate the volumetric flow of the fuel, and we can do it similarly as here. We will still use the heat input, but for the instead of the lower heating value in megajoules per kilogram, we will use megajoules per normal cubic meters, and then we will get normal cubic meters per second. And also the fuel consumption is often referred as not cubic meters per second but cubic meters per hour. So just multiply by 3600 seconds in 1 hour and we get normal cubic meters per hour. Now when we calculated the heat input, we can get to the thermal output, the Q heating. So first, since we have specified the electrical efficiency and also the efficiency of the overall CHP system, so we can get the thermal efficiency of the system. So eta thermal, which is just the overall efficiency minus electrical efficiency, because the electrical efficiency is efficiency of producing this product. The overall efficiency is this product plus this product, work or electricity plus heating. So the heating needs to be the overall efficiency minus electrical one. So we have 87% as the thermal efficiency, and from that we can obtain the heat output of the system. So thermal output is the fuel input multiplied by the thermal efficiency, and it's 4.8 kilowatts. And we can also get the mass flow rate of the water, which will go through the system, the heating water. Let's call it water, perhaps like this. And For simplicity, we will assume that the water has CP of 4.2, and you know that it works that the Q is m CP delta T. So the mass flow rate would be the heat divided by CP and delta T. CP we said that is 4.2 kilojoules per kilogram in Kelvin, and temperature difference is temperature at the output minus temperature at the input. Yeah, one more bracket, and we have the result in kilograms per second, or we can also have kilograms per hour. Okay, so now we have solved the energy balance of the Stirling system, of the Stirling unit by itself. And now let's have a look what happens if we have the additional peak boiler. So here we have the balance model of the additional peak burner, where we have some additional heat input, and we get the additional heat output and some extra heat that would go as the loss. So first let's have a look at the peak burner by itself. And in the problem statement there was that the heat output of this system is 15 kilowatts. And the efficiency, thermal efficiency of this system, of this peak burner, was 90%. So what we are missing is to get the required fuel input. So Q fuel, and it will be the thermal output divided by the efficiency. These were the input values, and we get 16.7 kilowatts as the required fuel input. And now, in the end, we will have a look at the performance of the overall system when the Stirling engine unit and the peaker system is combined. So basically what happens, we will enclose the Stirling engine CHP system and the peaker burner into a single box, and we have the combined heat input and combined outputs. So the Q in will be the fuel input of the peak burner plus the fuel input of the CHP unit. So it's 22 kilowatts. Then the heat output in the useful heat will be the 15 kilowatts from the peak burner, and then we have the thermal output of the Stirling system. And the electrical output will remain the same as the Stirling engine system, because we have it over here. We neglect any parasitic consumption of the peak burner. Let's say that it's just 0, so it will stay the same. In real situation it might be slightly lower because of other electronics controlling some valves, maybe some additional small pump for the circulation of the water and so on in the peak burner. But we will say that the power output will remain the same. So now we have the whole system heat input, heat output and the work output, and we can get the efficiency for heat production and efficiency for power production. So first, efficiency for the heat production is the heat produced, Q out, divided by Q in of this combined system, and the efficiency of the power production is the work or power produced divided by again the heat input. So we can see that when we need the additional power, so the overall thermal efficiency will be about 90%, just below that, but the electrical efficiency will drop to less than 5% from the original 18%. So this was the example for the Stirling engine. Now we will look at the second topic of our today's tutorial, which is CHP systems based on internal combustion engine. With the internal combustion engine, you can have the systems going from power output of several kilowatts, like micro CHP systems, like would be example over here. But the range is pretty wide, and on the other side of the spectrum can be systems with power output of several megawatts. The largest unit from, for example, company Tedom provides 4.5 megawatts of electrical power output, as is shown over here. Now, what does the CHP system based on internal combustion engine contain? Well, of course, the first thing is the internal combustion engine itself, but then there is lots of other auxiliary equipment, like you can see here, some pipes, dampers, supporting structure. For the CHP application, you need heat exchangers to exchange the heat from the flue gas or engine cooling to your heating fluid. Then you have some systems necessary for the exhaust gases, like the catalytic converters. You can see, for example, also some filter, flywheel if you have a small amount of the cylinders, so it's especially important to have smooth operation. And when these systems consume gas or any fuel, so you need the fuel handling system. Talking about the fuel, the combined heat and power systems based on internal combustion engines can use both liquid fuels, like diesel or heating oils, or gaseous fuels, typically natural gas. Now let's have a look at the typical configuration of the CHP system based on internal combustion engine. So we have the engine itself, the engine block, where are the cylinders, where are the cylinders with the pistons. Then the shaft would be connected most likely to some gearbox, and then via gearbox connected to the generator that makes electrical power. Now the engine will have some exhaust for the exhaust gases that can go into the heat exchanger for the heat recovery before it goes to the ambient. But that is not the only source of heat that can be handled or must be handled. Additional heat source is the lubricating oil that also needs to be cooled. So that is this circuit down here, where you have small heat exchanger marked as oil cooler. And what you have here is marked as jacket water. It's some cooling water that here it goes first through the oil cooler, then it goes to the engine itself to cool the engine jacket, to cool the cylinders, and then at the end it goes to the heat recovery heat exchanger, where the high temperature heat is used to transfer its potential into the heating water. Now with this hot water, it can go to the customer, it can go to the heat demand, for example some heating, process heat, etc. But if you don't have the demand for the heat and still you want to operate the system, you need to have some excess heat exchanger, because you always need to operate the cooling of the oil, the cooling of the jacket. Just you can bypass the recovery heat exchanger, but the heat from the lubrication cooling and the heat from the jacket cooling needs to be rejected for operation of the engine. Now some typical values of the heat and power regarding how it gets converted by the internal combustion engine. So in rough calculations with power outputs of, let's say, dozens of kilowatts, the efficiency of the internal combustion engine can be, efficiency of electricity production can be around 1/3, let's say 30–33%. Then another third of the heat is typically contained in the exhaust gases, and the last third of the heat is going into the lubricating oil and into the jacket heating. So this is a rule of thumb of how the heat in the fuel is converted and how it's distributed between different streams. Now we will calculate an example of combined heat and power system based on internal combustion engine, where we have the information that the internal combustion engine combusting natural gas has net electrical output of 104 kilowatts, and the exhaust flue gas has temperature of 552 degrees C. The fuel, which is the natural gas, is consumed at the rate of 28.3 cubic meters per hour, and our task is to estimate total efficiency when this system would be operated as CHP unit, micro CHP unit, or well, 400 kilowatts it is already standard CHP unit, with flue gas outlet temperature of 80 degrees C. Also, for the important nodes of the system, we will estimate the heat and mass flow and thermodynamic parameters. And we will assume two cases. First, when the jacket cooling heat is not used for the heating. For example, if we need some really high temperature heat, well, this would not necessarily be the case here, as we are able to cool down the flue gases to 80 degrees C, but just for illustration, we will see what would be the result if the jacket cooling heat and the lubricating oil cooling heat is not used. And then when this jacket cooling heat is included in the heating output. And the assumptions that we will consider is that the efficiency of power electronics, like the generator and some other electronic systems, will be around 96%, and mechanical efficiency of, for example, the gearbox and clutch would be 99%. Additionally, we will assume that there is no heat loss to the surrounding environment. All the heat is rejected in the defined heat streams. Now let's have a look at the balance model of the internal combustion engine used as the CHP system. So we have the engine block itself over here. This is the engine. we have some heat input in the fuel. Then the engine itself is hot, so it's rejecting some heat into the environment. This heat would most likely not be usable in any forms and any ways, because it would be some cooling air going around the engine at very low temperatures. Then at the engine we will have some work as the output. Work of the engine as mechanical work. But before this work will go to the generator, there will most likely need to be some gearbox. And the gearbox definitely will have some efficiency lower than 1, so it will also create some waste heat that will be rejected into the environment without any use, so another loss of heat. And then at the outlet of the gearbox there would be some generator. And the generator is the component that produces electrical output, the output that we want to get. Then from the engine will definitely go out the flue gas. That will go into some flue gas heat exchanger. And from the heat exchanger will be the outlet, the heat that we want to get. Some useful heat, and the remaining of the flue gas will also contain some heat and be rejected, contain some heat that will be rejected into the environment, because the flue gas will just go to the ambient atmosphere, so it would be other lost heat. This is the stack loss. So that was the flue gas. Then we will need to have some jacket heating and lubrication oil heating. Then we will need to cool the engine, cooled by the jacket cooling water, and also cool down the lubrication oil. So this would be cooling, from which goes some heat also, and it's the jacket. Plus the lubrication oil. And this heat can also go via some heat exchanger, or maybe it can be used directly. It's, let's say, optional. It's optional for the jacket cooling. The oil will definitely have some heat exchanger on the way. But anyway, this heat will need to be either rejected to the atmosphere, or if our heating demand is at sufficiently low temperatures, so it can be useful. So this useful heat is at high temperature, HT, while here we have Q useful at low temperature, or eventually it needs to be still rejected to the ambient, and it would be lost. Now, if you want to reject this heat into the atmosphere, you would still require some cooler, usually with some fan. So just take into consideration that if you do that, you still might need to have some work, some electrical work for driving the fan and pump and so on. And now this whole system, as we have drawn in here, is the internal combustion engine CHP unit. Just to make sure, this heat goes through the boundary, this heat goes through the boundary. This is the input going through the boundary of the internal combustion engine CHP unit, and these heat streams go also through the boundary of the system. And just to have everything, so here we have some mechanical power. Then, after the gearbox, we still have some mechanical power on the shaft. This is mechanical at the engine. This is mechanical at the shaft to the generator. And after the generator, we have the electrical power output. And we can look at this flue gas as also some heat flow, as heat flux of the flue gas, and this heat flux of the cooling. So now we have put together the balance, the schematic balance model of the system, and now we will add the calculations of each stream and their parameters. So let's start with summarizing the input parameters, which was the electrical power output, 104 kilowatts. Then we had the volumetric fuel consumption, which was 28.3 normal cubic meters per hour. Then we had the temperature of the flue gas as 552 degrees C, and temperature of the flue gas at the outlet of the flue gas heat exchanger which was 80 degrees C. And lastly, we had specified efficiency of power electronics. And generator to be 96%. And mechanical efficiency of the gearbox as 99%. We also know that the fuel is natural gas, so we can get the lower heating value of natural gas as 35.8 megajoules per normal cubic meter. And those were the all inputs that we had specified. Now, if you want to get the fuel input, volumetric consumption of the natural gas to heat input. So heat in the fuel would be the volumetric consumption, normal cubic meters per hour, divided by 3600, so that we get normal cubic meters per second. And we need to multiply this value with the lower heating value of the natural gas, so that which should be also in, if we want kilowatts, so we should get lower heating value times 1000, and we will get kilojoules per normal cubic meter divided by normal cubic meter per, and now second, and that will get kilojoules per second, which is kilowatt. From this we can get the net electrical efficiency of the system, because we have the electrical power output divided by the heat input, and we get the electrical efficiency as 37%. The parameters are taken from some relatively new engine, so you can see that it's close to the 33% as 1/3, as I told you about the rule of thumb of conversion of the heat input into different products. Also, when we have the electrical work, so we can get the mechanical work on the shaft after the gearbox. So work shaft after the gearbox would be the electrical output divided by the efficiency of the generator and eventually other power electronics. Then we can get the work of the mechanical power output of the engine, which is the work at the gearbox outlet, gearbox output divided by the mechanical efficiency, and this is the mechanical power output at the engine outlet, and we can also get the thermodynamic efficiency of the cycle. Which will be this value divided by the heat input. So we have solved the chain of values going to the electrical efficiency, and we got the fuel input. Now what to do with the remaining two parameters, the flue gas and the cooling jacket. Also, probably we should add that this Q loss from the engine itself would be neglected for this example, because it was not mentioned in the problem statement, and for simplicity we will exclude that. So let's call it Q loss engine, and it will be 0. So now we will use the parameters of the flue gas, which is the temperature difference, to get the heat contained in the flue gas. But for that we will need to do some more calculations, because the flue gas will have quite specific composition, and we will need to calculate it. Also, to get the mass flow rate of the flue gas, we will need the mass flow rate of the fuel going into the system. And in order to get the mass flow rate of the fuel, of the natural gas, we will need to get its density. And we have the natural gas consumption specified with respect to normal conditions, which are 0 degrees C and 101.325 kilopascals. So let's get the density of the natural gas, which we will assume that is pure methane at normal conditions. So the function will be props SI, where the output parameter will be density, with the input parameters being pressure, 101.325 kilopascals, but we need to insert it in basic units in pascals. Then the second will be temperature, which is 0 degrees C, 273.15 kelvins, and the fluid will be methane. And we get about 0.72 kilograms per cubic meter. So then the mass flow rate of the fuel will be volumetric flow rate of the fuel, which we have over here, divided by 3600, so that we get it. We get normal cubic meters per second, and then multiplied by kilograms per cubic meter, and we will get kilograms per second. But now, to convert the fuel into the flue gas, we will need to use the stoichiometric calculations. So in order to get the composition of the flue gas, let's first try the stoichiometric equation of combusting the methane. So the methane has molar weight 16. So 16 kilograms of methane plus 64 kilograms of O2 because per 1 molecule of methane we will need CO2, so 1 molecule of O2 per the carbon, and then 1 molecule of O2, 2 atoms of oxygen per 4 atoms of hydrogen, so that we get CO2 where for the CO2 we will get 1 molecule, and the CO2 has molar weight of 44. And then we will get water, which has molar weight of 16, but we get 2 molecules, so it's 36 kilograms of water. Now, if we want to get the values per 1 kilogram of fuel, so 1 kilogram of fuel would need to be combined with 64 divided by the 16 kilograms of oxygen, and we would get 44. Again, we have it calculated with respect to kilogram of methane, so 2.75 kilograms of CO2 and 2.25 kilograms of water. We can also check that the products are the same as the reactants are the same as the products regarding the weight. So here we have 80 and 80, here we have 5 and 5, but we will not combust the methane with pure oxygen, but we will use air. So let's also write what we will need for the air, where the air has following contents: nitrogen, oxygen, argon. We will assume that there is no CO2 and that it's dry air, so that there would be no water, but the water will be later on in the products. Now we will also later on need the molar weights. So the nitrogen has 28, oxygen 32, argon 40, CO2 44, and water 18. And we will want to see what happens if we combust 1 kilogram of air with the stoichiometric amount of CH4, because the engine would most likely work with very close to stoichiometric amount of the air. So 1 kilogram of air goes to flue gas, but before we do that, let's do it like this. And let's write mass fraction of the air for the components. You can find it in many resources, or you can also recalculate it from known volumetric content, volumetric fractions. So nitrogen, oxygen, argon will be 0.0132, and as we said, CO2 0 and water also 0. And these are the input values, these also. And we will also, in this stoichiometric equation, have a look what would happen if we have 1 kilogram of air. Which means that we will have 1 times the concentration of oxygen, kilograms of O2, and that means that we will have either this, or we can also have it with respect to this one over here, times the content of the oxygen divided by the 4 over here. And for purpose of later using this equation, we can also put these two values, we can log them. And anyway, we can see that for 1 kilogram of air, which is 0.2317 kilogram of oxygen, we need 0.058 grams of CH4 for stoichiometric combustion. And on the side of the products, we will get this amount of CO2 and this amount of water. We can also check that this was empty, but here that we have the same values. So let's just highlight this equation which we are using, where we are calculating the amounts with respect to 1 kilogram of air. So from the air that has this content, let's write here also some auxiliary parameter. Some to check that everything is in order. So when we combust this air in stoichiometric amount with the methane, we will get, and now in the flue gas, where at first per 1 kilogram of air we will get the same amount of the nitrogen. The oxygen will be all combusted, so it's 0. The argon will stay, nothing happened to that one. And for the CO2, we have the product over here. And for the water, we have the product over here. And get the sum, which should be basically 1 plus the amount of the fuel. And now, if we convert that to mass fraction, so we just take this value and divide it by the sum over here. And let's check it out, and we can see that we have mass fraction of each component in the flue gas. For more exact calculations, and also for example to get the dew point of the flue gas, we will need as intermediate point to get the molar mass of the flue gas. So molar mass of the flue gas, it will be determined as 1 over sum of the mass fractions divided by the molar weight. So mass fraction of here the nitrogen divided by molar weight of nitrogen, mass fraction of oxygen, molar weight of oxygen, same for argon, here CO2, and finally water. And we get the molar weight of the flue gas as 27.7 kg per kilomole. And now using this we can get also molar fraction. Maybe let's put this for clarity a little bit down. Yeah. And we get the molar fraction as the mass fraction multiplied by the molar weight, which we can log, divided by the molar mass of the component. So we get the molar fractions. Again, let's check that we get, as the sum we get to 1. And now when we have molar fraction, we can get also the partial pressure. Or maybe just directly in pascals. So also into the general specification of the problem, let's add the ambient pressure or the flue gas pressure, the overall one, where we will consider that it's at the standard pressure 101,325 pascals. And then the partial pressure is the molar fraction, which is the volumetric fraction times of the component multiplied by the overall pressure. And now, when we have the partial pressure, so we can calculate, we have pressure, we had the temperature here and here, so we can calculate the enthalpy of each component. So, let's say enthalpy, HI, and let's do it this, joules per, or maybe let's go for kilojoules per kilogram. And the enthalpy will be function props SI where the output would be enthalpy based on pressure, which is the partial pressure, and temperature, which we have over here for the flue gas inlet. We can log this, and the fluid would be the nitrogen. and let's also HI at the of the flue gas. And we wanted the enthalpy in kilojoules per kilogram, so divided by 1000. Oh, and one more thing, the temperature should have been in Kelvin, so plus 270, 3.15. And now we can extend this function also down. Just for the oxygen it will not return correct value because the oxygen has zero partial pressure, the oxygen is not present. If we consider completely stoichiometric combustion, and we have the argon, CO2, water. And now to get the overall enthalpy of the gas, so we should take sum of the enthalpy plus the mass fraction. So it would be this, enthalpy multiplied by the mass fraction of the first component, second component, third component, and last component. So we have the enthalpy at the flue gas inlet. Now enthalpy at the flue gas outlet. Enthalpy I acids per component, and it was flue gas out. Again, kilojoules per kilogram and Kelvin, and basically we can take the same function as we had over here. Just the only thing that we will switch is the temperature. And now in here the mass fraction will stay the same, just the enthalpy would move by the one cell to the right. So let's just log the first values, and so let's log the fraction, the mass fraction values, 2, 3, and 4. And we get the enthalpy at the outlet. And now we can have the difference in enthalpies. Delta H, which is the enthalpy at the inlet minus enthalpy at the outlet. Again in kilojoules per kilogram. So this will help us to determine how much heat is in the flue gas. Specifically, how much heat are we able to use. But now let's also do some more verifying and informative calculations with the flue gas. For example, we can check where is the dew point. So the dew point temperature, let's have it in degrees C, will be based on the water content and its partial pressure, and it can be used as, it can be found as function of at the saturation level of the for a given pressure. So props SI, the outlet is temperature based on pressure, which is the partial pressure over here, and quality, which should be 1, and the working fluid is water, and this is in kelvins, minus 273.15, and we get the dew point temperature to be 60 degrees C. So also our method of calculation was correct, because at the 80 degrees C the condensation would not start yet. Now what if we wanted to get the enthalpy at, for example, 20 degrees C, but for calculation where the water would still not condense, so calculation with respect to for balance calculations with respect to lower heating value. So let's say enthalpy I at 20 degrees C, non-condensing, kilojoules per kilogram. So for most of the calculations it would be same or similar. You would still get the enthalpy based on the pressure and temperature. The temperature would now be the 20 degrees C, and yeah, here was the component name, and the function would be like this. But once we get to the water, we would get the temperature of the condensate where all the water already condensed. If we want the water to be still considered to be in gaseous phase, we can get approximate value where we get the pressure at some point where the water would be still in vapor form. For example, at 20 degrees C, something like 2 kilopascals should be still okay. And then we would calculate the enthalpy as we did before. If we would like to get the value of the enthalpy when the water would condense, so we should actually do the iteration back, because the partial pressure of the water would be exactly on the saturation point, and some of the water would be in gaseous form and some of the water would be in liquid form. So the liquid form needs to be handled separately, and the gaseous phase would be handled separately based on the mass of the condensed water and mass of the gaseous water. Okay, now we can continue. We have the difference in enthalpy of the flue gas, but we will also need to get its mass flow rate. we had the mass flow rate of the fuel over here. And let's just do one more thing, where we get amount of air per 1 kilogram of the fuel. So something we had over here. 1 kilogram of methane resulted in 4 kilograms of O2. And if we want to get kilograms of air, so we would get the 4 kilograms divided by the oxygen mass fraction in the air, and we would see that we need 17 kilograms of air. So the mass flow rate of the flue gas will be mass flow rate of the fuel plus mass flow rate of the fuel multiplied by the amount of air that is needed per 1 kilogram of the fuel in kilograms per second. And now we can calculate the amount of heat that is, first the heat that is in the flue gas when it's cooled down to the reference temperature, 20 degrees C. So let's call it Q flue all, which would be mass flow rate of flue gas multiplied by the enthalpy difference flue gas inlet for some heat exchanger, outlet of the engine itself, minus the enthalpy at 20 degrees C when the water would not condense. And the amount of heat from the flue gas, which we can use by our CHP system, which is mass flow rate of the flue gas multiplied by the enthalpy difference flue gas from engine minus the flue gas outlet at 80 degrees C. When we are summarizing the losses, so, well, the first loss was directly from the engine. We considered that as 0. That's Q loss E. It was the 0 from here. Then we have the Q loss from the gearbox, which is 1 minus the efficiency of the gearbox multiplied by the work at the engine output. So it's about 1 kilowatt. Then the heat loss in conversion from mechanical to electrical and electrical conversions like generator and some power electronics. So Q loss, let's call it electrical, which is the work at the mechanical work at the shaft going to the generator multiplied by 1 minus the efficiency of the generator and related systems over here. That's 4 kilowatts. Actually, we did not have it in the figure over here, so let's just add it. So it was that. Then the heat loss in the flue gas and the stack loss. which is the difference between the heat content in the flue gas and the actually used heat from the flue gas. And now we can also get the amount of heat in the cooling of the jacket and oil. Which is, if we have a look at the balance model, so we have the heat input minus the heat losses over here minus the work output and minus the flue gas. So we have the heat input into the system, which was in fuel over here, and now minus heat loss directly into the environment, which was 0, then the work at the shaft directly at the engine outlet, and minus the heat in the all the heat in the flue gas. So you can see that for this engine the work output was a little bit over 100 kilowatts, 104. Then in the cooling system is another 100 kilowatts, and just in the flue gas, as the temperature is here not that high, so the amount of heat in the flue gas in this case is a little bit lower, at 64 kilowatts. And now just please note one thing: the electrical loss, I had it referenced to wrong cell. It should be the work of the shaft, work on the shaft after the gearbox, multiplied by the electrical efficiency, and the work of the heat loss at the gearbox should be, as is correctly here, referenced to the work at the engine outlet. And now we can finally get the efficiency of the system. We already have the electrical efficiency, which is 37%. Nothing will change on that, regardless of how we use the heat. But the thermal efficiency, first for the case 1, when the jacket cooling would not be used. So the thermal efficiency would be the heat of the flue gas that is used divided by the heat input into the system, so Q fuel, and it would be 20%. Then the efficiency for the second case. So in the second case we are using both the heat from the flue gas and the heat from the cooling systems, and this divided by the heat input, and we get almost 59%. And now let's have the total efficiency of the CHP system, and also for the first and second case, where for the first case it's the efficiency of producing heat plus the efficiency of producing power. And for the second case, it's the efficiency of producing heat here plus the efficiency of power production. And there we get that the overall efficiency is almost 96%. And just last thing, that if we want to make sure that everything is correct, we should get the same values of efficiency also as the sum of the product, which is the Q flue gas CHP plus the electrical output divided by the heat input in the fuel. And we can see the same value. And the same needs to work also for the second case, where just we add as the other product also the heat from the cooling system. So we have successfully calculated the balance model of the CHP system, where the important message to bring from it is that the overall efficiency looks very nice, but only in the case when the jacket cooling and oil cooling systems, when the heat produced by the system is used. If this heat could not be used, so the value of the overall efficiency would be much smaller, and the economy of the operation would probably not need to be that good. And that is the case especially when we need high temperature heat, which can be extracted from the flue gas, but the jacket cooling and oil lubrication oil cooling system cannot go to high temperatures. So this heat would need to be rejected to the environment, and the overall efficiency would be low. Okay, so that's it from the tutorial for combined heat and power systems balance models.